next speaker, Sewon Min. She is about to join Berkeley, if not already, as an assistant professor in EECS, and is currently a visiting researcher at the Allen Institute for AI. So with that, Sewon, take it away.
Thank you for the introduction. Can everyone hear me? Cool. So I'm really excited to present my ongoing work. So this is not public yet, called Silo OpenLM Training Language Model on Silo Dataset. And this is a joint work with Weijia, who is sitting here, and Akshida and Kevin, as well as a few collaborators at AI2 and some outside of AI2. So before I start, let me make a few points so that we can use it as a common ground to motivate our work. Data is very important. I'm sure you may have heard that you improved model architecture and training, and maybe you had a couple of points gains, but if you slightly improve the data, and you have more than 10% gains. So data is very important as a pre-training data of the foundation model. Data is also secret. So you may have seen technical reports from frontier labs like Llama and DeepSeek, which share surprising level of details like model architecture, training recipe, and even all the hyperparameters. And the one thing they would never share is what data they use. And somehow related to this, a lot of data, and especially valuable data, is often proprietary. And what that means is that it's the data that is not publicly available so that you can just simply download, but it's some data that you have to purchase or have a negotiation with the data owners. And a lot of data sources that are known to be high quality, such as news, books, textbooks, and some educational content, are proprietary. More interestingly, even the data that used to be public is becoming proprietary because the data owners realize their market value of their data and is shutting down their data. For instance, you may have seen some data providers like Reddit and Stack Overflow are now shutting down their data and charge for their data. There is a very great paper from Shin Longpre et al. Called Consonant Increases, where they studied this phenomenon. This is one graph from their work where x-axis is the year, and the red area means the data is protected under some restriction. So you can see the red area is growing and growing, especially after the advent of ChatGPT. So given this data landscape, how can a research community make a progress? I think there are a few options. First, obviously, I think we should continue to make progress to develop open source training data so that everyone can build on that. AI2 has been working on that, and then there are many other amazing work on that, like DCLM and Red Pajama. But the second approach that I think is as important and is less explored is to admit the fact that some data sets will remain to be proprietary, because that's just how the world is, and to think about the new classes of model architecture and training method that can accommodate this data landscape. And this is going to be the main topic of my talk today, so I'll talk more about what exactly this means. And in particular, I'll start with this point. So far, we've been assuming that the access to the data is binary, either available or not available. And some of you may think, of course it's binary, how can it not be binary? But I'll claim that this is not binary, it's rather a spectrum. And there are many scenarios between these two cases. Let me give you a few concrete examples. There are some cases that the data owners want to have full control over their data, so they don't want to share the data or sell the data. However, they might be okay with training the model on their data locally and then share the model trained on their data. And in this way, they can still sell the impact of their data while having full control over their data. Here is another example. The data owner might be okay with sharing the data, but it comes with various restrictions. For instance, they may say the data can be sitting in a very specific location, like a very specific AWS or Google Cloud. And some of you might think these look like an arbitrary cases, but these are actually very, very common. Even at AI2, there are many data negotiations going on, and we do have very specific cases that fall into these cases. And these are just examples. There are many other possible restrictions. For instance, the data may be available across different times. The data might expire, or the owner of the data might request opt-out later on. So I hope it's clear to you that when we say data is available, we're actually making a lot of assumptions. We're assuming that the data is all available at the same location so that you can take a union of them and randomly shuffle the data so that you can use to pre-train a large language model. We're also assuming all data is available at the same time and the data is available forever. For instance, it doesn't expire and there wouldn't be opt-out request. But all of these assumptions are pretty strong assumptions and are just not realistic. So here is the research question. When we can't train on all data sets jointly because they are not on the same location, how can we still develop the model that can benefit from this siloed data set? And we still want the eventual model to be a general purpose language model that can be public. And just to make the setup more concrete, here is a concrete setup. We assume there is some public shared data, like Common Crawl, where everyone can download and use it. And then we can also train a large language model on this public data. So this model is completely public. And then we have a set of entities that have their own data, but this data is proprietary and remain to be private. So whatever data remains local, it's not the public data. And then each entity can take the public model and then do continuous pre-training on each of their siloed data set. And this training is local. Each entity who has the data trains the model, not in the public space. And once you have this model, you can share this back to the public. So back in the public space, you end up having a set of models. One will be the original public model, the others are from the data owners. And eventually we want to have a combined model that is a single general purpose model. And anyone can use this model. And importantly, we will hope this combination process is free or cheap because we wouldn't want to go through the expensive process over and over whenever there is a new participating data coming in. So just as a summary to reiterate the requirements, we want to train on isolated data sets called silo data sets. We want each training to be in isolation. There is no joint training. We want the resulting model to be public general purpose model. And also importantly, we want to support data opt-out, and adding the data or removing the data should be free or at least cheap. I also want to mention federated learning, since some of you may be curious how is it different from federated learning. The federated learning can also train on siloed data sets, so it satisfies the first condition. However, importantly, all the other requirements are not made in federated learning. For instance, federated learning train on all siloed data sets jointly by injecting noise to the gradients in a privacy-preserving manner. That means there is a communication cost because these data sets are sitting in different places. And in language model pre-training context, this is not very practical because small change in training efficiency matters a lot. And in addition, it cannot support data opt-out or data addition. Whenever you have a new data coming in or need to remove the data, you have to retrain from scratch. Yep.
What's your sense of how current commercial providers like OpenAI and so on are oriented towards this problem? Like, have they, do you think that they're bottlenecked by this? They don't really care? And then, like, also, if you make progress on this problem, how do you think that'll change what they actually do?
Yes, that's a great question. So first of all, I've never been to a frontier company, so I don't know what they're doing. But I think it's sort of well known that they're not just training on public data like Common Crawl. So they're definitely collecting proprietary data sets. And if you are a company that has a lot of money, then you can probably negotiate the data or purchase the data. I think the recipe that we have can still help them because it will make the data negotiation easier. But also we are trying to find a way that can still benefit from proprietary data without needing to purchase the data. Any other questions? Yes.
So the data that large private models use is not available. But is it okay or good idea and also legal to just query them to get that data and train a model on that? I
see. So the question is, if you have have access to the frontier model that probably have trained on a lot of data set, and if you generate the data, then it's fine. I'm not really sure about the legal context. I think that is possible, and if you created the data in that way, you can think of it as also the data that you made. So I think that should be possible. But I think if people do that, then it also costs a lot of data. So that synthetic data can also be seen as some proprietary data in some sense. Okay, I'll move on. Yeah, so and just to move back, before moving to the modeling section, I want to describe the specific experimental setup we did for this work, because I think seeing some of the concrete data sets could help. So for public data set, we use Common Crawl since that's a real public data that anyone can download. The choice of silo data sets was difficult because hopefully we want to use real proprietary data sets, but by definition, they are not available for us. But at the same time, we didn't want to just choose arbitrary data sets and consider them as proprietary because this is just not realistic. So in the end, we were able to choose 7 data sources that we think are realistic enough. And in particular, I want to highlight the 3 data sources in the second row because they are in fact actual proprietary data sets that you cannot download as of today. So for instance, the news articles was extracted from Common Crawl that we downloaded a few years ago, but these news providers now shut down their data and now protect their data from Common Crawl. So if you download Common Crawl today, you cannot see them. And similar to Reddit, we downloaded Reddit a few years ago when they did not have restrictions, but now they have restrictions. So we cannot really use Reddit for AI training if you download today. And textbooks were also something we internally obtained legally at AI2, but we cannot really release the data. The 4 data sources in the first row are simulated proprietary data in that they are actually public, but we think they are coming from the domains that are realistic. For instance, math and code are the capability that everyone cares about, but it's also very difficult to get public data that is high quality. So I'm sure a lot of frontier labs are using proprietary data for math and code. Similar to creative writing, we extracted them from Common Crawl, so it's actually public, but probably these are more commonly found on books. And similar to academic papers, we use open access academic papers, but there are a larger number of closed access academic papers. Any questions in this setup? Cool. Okay, so that was about the setup. Now the question is, so how do we design such a model that can benefit from it? So I'll start with surveying the existing work that could be relevant. And they can be largely divided into a task fine-tuning setup and a pre-training setup. So in task fine-tuning, this setup has been actually quite actively studied. I'll not go over too much detail, but I'll highly recommend taking a look at this paper that I cited, Yadav and Rafael et al. It's a survey paper that is very, very comprehensive. And what they typically do is to use LoRa adapters. So they train adapters independently and then merge them back. Now the problem is LoRa adapters are very effective for fine-tuning, but not for pre-training. So the recipe they have does not really apply to our setup, which is more about pre-training. So what about pre-training work? So we were not able to find the work that have relevant setup, but there is actually a line of relevant work on model merging. And typically people have been looking at model merging for boosting performance or for better specialization. So not exactly our setup, but we think they are relevant enough. So in the next few slides, I'm gonna survey what people have been doing for model merging. So the first category of work is something called weight merging and ensembling. And here the question is, when you have n different language models that are trained slightly differently, how can you merge them for improved performance? And there are 2 options. One is called weight merging, and the idea here is that you do weighted average over all parameters you have, so that eventually it's a single model, and then you make an inference over the single model, just like you would do for any language model. And the other approach is ensembling. This means you keep all individual models, you make an inference over individual models separately, and then you do weighted average over the predictions. So the only difference is when you do averaging, whether you do averaging in the parametric space or after you get the output. So I don't know how this sound like. Some of them may look a little arbitrary. For instance, why would you even expect weight merging would work at all? But these are actually pretty common practices in pre-training. People have been found it very useful for boosting performance at the late stage of pre-training when you have a few different checkpoints on slightly different data mixes, and then you can do weighted averaging, or also for specialization. For instance, when you have data like common crawl, you can divide them based on domains, train them separately, and then merge them for better specialization. So people have been looking to that, but in a slightly different setup.
But do you require the models to have the same architectures when you do the weight merging?
Yes, that's a great question. In order to do weight merging, the model should be in the same architecture. In fact, not just the same architecture. Usually, one of the requirements for weight merging to work is it should start from the same seed model.
Okay.
Yeah. Ensembling doesn't have that restriction because you can merge any output probability distribution.
Yeah.
Yes. Oh, question.
Can model merging be done with multimodal models and LLMs?
Oh,
the LLM is the same, but the vision tower or something is different.
That's a great question. Can we merge language model and multimodal model? I'm not aware of any work that did that. I guess one question is whether the architecture would be the same. If the architecture is same,
Assuming the LLM is the same.
I see. Then I think it could work. But I'll also show later, but weight merging work in very specific cases. For instance, when data mixes are similar to each other. So I think if one model was trained on language only and the other was trained on vision only, then it might have hard time doing weight merging. So this is like pretty empirical.
So I've always been curious, if people have figured out why this kind of like a simple approach works, like just merging the weights. Do you have any, given that you've worked on this for so long?
Yeah, that's a great question. Why is weight merging work? Because you didn't say that, but this seems like a pretty arbitrary method. Like it's not even clear why this works. My sense is it works in a quite restricted setting. Like it works only when a set of assumptions are being made. For instance, they really start from one same base model. And then I think the independent training cannot be too long. So only if it was trained for a little bit more, then they can be merged. And they can be merged when the data mixes trained to each are not too different. So I think it works in a bit specific scenarios, but it doesn't work all the time.
Yeah, I feel like the reason it works is just like taking average, that you reduce the variability, and then variation is part of the accuracy, so this is how.
Yeah, that was the classical reason, but
yeah.
Things have gotten so complex.
So. Yeah, right, yeah.
Question?
So, if you think of a language model, the output of a language model as an inference, and you have different language models, then you have different inferences, which may agree with each other or may not agree with each other, or partially may agree with each other, and so on and so forth.
Right.
So is averaging, which is essentially an arithmetic operation, semantically even the right operator to deal with the essentially semantic issues we are dealing with when we apply these models?
Yeah, that's a great question. My sense, I don't know if I have a good answer, but my sense is just uniform averaging is not optimal, but if you do weighted averaging, then it kind of makes sense because maybe some of those models are more relevant to the input query or not, and then if you're giving higher weight to that expert while not to others, then it seems to make sense, at least intuitively to me.
And the weighting could be learned based on how possible we might describe our confidence in each of the models.
Right. There are many different options for how to get weights. Yes.
I mean, sort of, the other aspect of the question was that, when these sort of differences occur, we are talking about disagreements, right? And then if we weigh things, we're not explicitly modeling disagreements.
Yes, that's true. Yeah,
It works out empirically and
Yes, I agree. In the sense that ensemble is just making the decision entirely independently without any like coordination between them, and then we are just like aggregating them in some way. I don't think we are like explicitly modeling disagreement. Maybe the later architecture that we'll describe has a little bit more complex architecture, and that can do that. I think this method in particular are very, very simple. There's no coordination.
Yeah, just a follow-up on why the weight merging is working. And I'm wondering whether this implies that the components that do some functionalities in the model doesn't change the locations, like it's stable in the locations of the sub-locations of the models.
Yeah, I think that's a great insight, and I still don't know the answer, but I agree with your intuition that I think what really matters is the initialization, and once you go through a few like steps, and we actually trained the base model for 1 trillion tokens, so if you have gone through the common training for 1 trillion tokens, then the parametric space is sort of fixed, and everything else is more of the small adjustments of that parametric space, and if you are already in the same parametric space, then maybe merging is easier.
I see. And also, another quick question, like why does what's the difference between training from this seed model and fine-tuning on the pre-trained model? Like
training the same model and fine-tuning on the
fine-tuning on the pre-trained model.
Oh, I see. So here we are assuming there is a base model and we are doing continual pre-training. Okay. So if we consider fine-tuning as just continuous pre-training, then it's the same. But the one difference is fine-tuning seems to typically refer to training on labeled data set. Here, everything is unlabeled data. Yeah, thanks. Yeah, I'll move on and take more questions later. So that was the one existing approach. The other existing approach that I want to mention is something called MOification. And I don't think this is an existing term, but I felt like this is a term that describes what is happening quite accurately. And again, here, the question is when we have n different language models, how can you combine it into a single model? And here is how it works. Let's say you have 4 transformer models like that, and then I have this arbitrary icon, but what actually it is it's a L layers of transformer blocks, and one transformer block has norm, multi-head attention, norm, and the fit-for network. And fit-for network is usually the largest portion in terms of parameter count. Now, what we do for MOification is we have a new transformer block. We copy each of FFNs, but keep them separately. We do weight merging for all the other layers, like norm, multi-head attention. And then we have a router. And this router basically takes the input from this shared layer and then consider which FFNs we should rely more on the other. So it assigns weight to each of the FFNs. For those of you who are familiar with MOE, and a few previous talks in this workshop also cover mixture of experts, the architecture is actually exactly same as mixture of experts. So that's why we call it MOification. We can just think of it as a different way of initializing mixture of experts. One caveat here is that you can remain the shared layers or FFNs frozen, or you can make it trainable, but it has a starting point, but the router does not have a starting point. So after you merge, you still need to train the router jointly over all data sets. So these are 2 different approaches, and as I mentioned, they usually did that for improving performance, but not exactly on our setup where there is a strict disjointment between isolated data sets. So now the question is, how can we apply this to our setup? And it's actually pretty straightforward. Just to recap our setup, we have a public data and then public model trained on this public data. We have a set of siloed data sets and then the model trained on each of them. And then these models will be gathered back in the public space. So in the public space, we do have a set of models, and now we can just apply existing model merging method. It could be ensembling, it could be weight merging, or it could be MOification. Now, if you think about it, you might have feel that weight merging and ensembling is probably less expressive than MOification. because MOification is actually a strict generalization of the other two. So we'll probably want to use something like MOification. However, this has a big problem, which is it's actually not exactly applicable to our setup. As I mentioned, because it has a router, you typically need to train MOE after merging on all datasets jointly. However, in our setup, we assume that each of the training data, which are silo datasets, strictly remain silo. So we can never merge them into a single dataset and train the router. You can still train it on public shared data only, which we actually did and compare with in the later slide. But this wouldn't work very well because it will always prefer to use public model. So that's kind of the background. And now I will talk about two new ideas that we added to MOification to make it really work in our setup. The first idea is what we call MOE-aware silo training. And here's what we do. Let's say there is a public model like this, and then when you are a data owner and you are training your model locally on your dataset, what you would typically do is you take this public model and then do continuous pre-training. Now, instead of doing that, what we propose is you copy FFN to make it a mixture of experts that has two experts. So now you have shared layers and then two FFNs every layer. And then you make sure the shared layers and the one half of FFNs remain frozen, so it's still exactly same as the public model, while only keeping the other half FFNs trainable. So these FFNs will be trained in a way that it complements the public model. Is it clear?
We just don't update the weights on the frozen FFN.
Yes. We don't update weights for the first FFNs and only train the second FFNs for every layer.
Are you routing the data to those two different FFN experts, or you really treat them as like always activated together?
So yeah, great question. We keep both of them activated together, but we still have the routers, and that router will decide on the weights. So for instance, it could choose to have higher weights to the trainable experts, but not to the frozen experts.
Is it a bit like putting adapters on FFN layers?
Putting an adapter to FFN layers.
Can the other FFN layer be considered an adapter?
Oh, I see. I think that's one way to say that, although I think when people say adapter, usually it's a small fraction in terms of number of parameters. Here it's different because FFNs is actually the majority part of the parameters. The shared parameters are actually small. Yeah, so you train the model locally in that way, and then there are other data owners that will do the same thing. So in the end, it looks like this. And then back to the public space, you will have a set of models that look like this, and then you will merge it to a single model. And then when you merge it to a single model, you take the blue part as one line of FFNs, and then which is just the public model, and then you do the same for green, yellow, and red. So it can be easily combined into one model. You don't even need to do weight merging because the shared layers are already identical. So you just can take it. The blue part, you can also just take it because they're all identical across different models.
How do you make sure the router are assigning like score of equivalent scale?
Yeah, that's a great question. So this is like something I didn't really put in the architecture, but what happens is that when you do like training locally, your router is basically a two-way classifier, right? And then you can think of it as having two vectors that represent one FFN and the other FFNs. We still keep one vector frozen while only keep the other vector trainable. So each of these models have two vectors, and then when you combine them, the router also can be merged. So now you're merging three two-way classifier into a single four-way classifier.
So you train the green one on the same data set as the blue one, like as the first phase?
Oh yeah. So the blue part, we can say it's only trained on public data sets because these blue parts were from the model trained on public data only, and they remain frozen. So they haven't really trained on any silo data set. And then only the green part has seen the silo data set for the green entity, but then there is yellow entity and orange entity, they have their own data set.
Makes sense.
Yes. So like for instance, you could imagine if you're removing this red part, then the rest of the model has never seen the red data.
Makes sense.
So also FFNs are in the same layer of different layers.
Oh, sorry?
Also FFNs are in the same layer of different layers.
Oh, I see. Oh, each layer has FFNs, and then FFNs across different layers are different parameters. Is that your question? Okay, yeah, so just to continue, so the reason we want to do that is really to make sure that there is no need for training the router after merging, because the whole reason we've been doing this is because we can't really train the router after merging, since we don't have access to all data sets. And it will show the result later, but it works quite okay even without router training after merging, so that's good. However, when we did an error analysis based on this model, we found that a lot of errors are still coming from suboptimal router decision. So there was a significant room in improving the router. So now the second question is, then how can we improve the router decision? And then that leads to our second idea, which we call obtaining proxy data to silo datasets. And here's the idea. We couldn't train the router because we couldn't take a union of silo datasets. But can we find a small subset of public dataset that looks like each of the silo dataset, and then use it as like a proxy silo dataset, take a union of them, and then train the router? And if you can, the router is like very small portion, so you might not even need a lot of data. You can just have a very tiny fraction of data and then do that. So for instance, that's what we did. So for instance, let's say you are a data owner that has textbooks. So you train your own model, which is this. But then at the same time, you're also training a classifier. And this classifier is supposed to distinguish public data from your own textbook's data. Once you train this model, you make an inference by feeding common crawl to the classifier and take a tiny fraction of common crawl that looks like textbooks. So the way we can think about it is that the common crawl is probably not going to take textbooks because these are just web pages. But there might be tiny data that we can find that looks like data. So it's not enough to train the whole expert, but large enough to train the router. So usually less than 1 billion tokens, usually not enough to use as a pre-training, but okay to train a small part of the model. Yes?
So is it another way to do this could be to use synthetic data, but is that a strategy you didn't go for because these individual owners may not have access to good synthetic data generators or something?
Yes, great question. Yes, we can do synthetic data that looks like silo data sets. That's actually a good thing that we could probably try. I think normally, with the limited information about silo data set, it might be very difficult to generate synthetic data that looks like silo data.
You query the model that is trained on it.
Oh, I think that's very difficult. Like people have tried to do training data extraction, meaning you query the model many times to extract the training data, but the success rate is very, very low.
So when you say look like, is it in the format? Like what if the silo data have some specialized knowledge that doesn't include in the common crawl?
Yeah, that's a great question. I think when we say like, it means like similar format or similar domain. Now I agree with you that probably the reason it's silo data is because it has something special that is not in public, like special knowledge. That wouldn't be in the subset of common crawl. But actually, I think that is an important point that we have to do all of things. We use this fraction of data only for router training. So we use that to decide which experts to use. But the expert we use, like FFNs, has to be the FFN that is trained on actual silo data set, because probably the knowledge are stored on FFNs. The router is only to decide which experts we should use.
I see, yeah.
Maybe I'll finish the idea to answer more questions. So yeah, so this is how you get the subset of common crawl, and then now I'll describe how you can merge them. So in the public space, you have a set of pairs of the model trained on each of the silo data set and the proxy data. in terms of model merging, it's exactly the same as the idea one. You can just take it to make it a single mixture of experts-like model. But then after merging, you can continuously train the router. And the way you train the router is a union of this proxy data set. And importantly, all the other layers like FFNs remain the frozen. So router just decide which experts to use. Oh, question?
You train your router in a supervised way that you tell it from which source is it, or do you just try to maximize the overall performance when you go through it?
Correct question. Our objective is just next token prediction, so we doesn't do any supervised training. And we think that's a more natural way to train this because it will be very difficult to choose which one is the right expert. And another important thing is in the analysis, we found that the router decision is different across different layers because which router is most important one can change over layers.
Is your classifier like some kind of the information retrieval system that retrieves some textbook-like documents from the common library?
Oh, I see. That's a great question. I guess you mean the previous slide. The answer is no. We just use a typical two-way classifier that is trained. But I think classifier approach is actually the one of many possible options that can extract a portion of relevant data. So we can also use retrieval to do that. Okay, so I'll move on. Yeah, so this was two ideas. Now I will move on to experiments. So I just put all the details of our experimental setup. You probably don't need to read all of them, but the main point is we used the 7 billion parametric model. We just copied the architecture and all the hyperparameter from the existing 7 billion model. And then in terms of how long we trained, we first trained the public model, trained on public shared data for 1 trillion tokens. And then we assumed that each of the data owner is doing continuous pre-training on each of the silo data set for 50 billion tokens. And then we merge them. And in the case that we do router training after merging, we train for 5 billion tokens. So this router training is pretty lightweight. Okay, so here's the result. And normally I don't want to put a huge table in the presentation, but for this presentation, I thought maybe looking at some numbers could be helpful. So I'll try to go over it one by one. So we tried a lot of benchmarks, tried to be representative and use the standard benchmark used for a pre-training model. So for instance, we use Core 9, which is actually the average of 9 data sets that are commonly used to benchmark pre-trained model. We have a range of MMLU and MMLU Pro data sets. I just named a few subsets that have some interesting pattern. We have AGI eval, which is one of the challenging benchmark. Big Bench Heart, which is also a benchmark that is quite challenging. And we also have some data sets that look into specialized capability, like GSMAK and math for the math capability, and the average of for coding task for coding capability. And then I also have an average because I think you might want to see the single number, but sometimes I feel like average is a little misleading. So these numbers are the performance of the public model that is only using the public data. And maybe something that is worth remembering is if you don't do any of this, then the only public model you have will be this model, the model trained on public data only. So this is our baseline, and everything what we do later is to be better than this public model. Okay, we also want to look at the individual experts, meaning the model that was continuous pre-trained from the public model on individual silo dataset. So we first have textbooks experts, which is trained on textbooks as a silo data. We found that it improved performance a lot on some of the key benchmarks, such as MMLU biology, CS, economy, engineering, and Big Bench Heart. And then the gains were quite significant. And these really indicate the value of having access to proprietary data set. Now, if you look at the average number, then you can see it's quite close to a public model, so it's not that good. And basically what was happening is that for data sets where textbooks are not relevant, it drops the performance a lot. For instance, for Core 9, it drops by 5%. For MMLU politics, it drops a lot because our textbooks probably doesn't cover any topics about politics. Now, the same thing happens for math experts, which means the model was continuous pre-trained on math data. It helps a lot of math-related benchmarks like MMLU engineering, Big Bang chart, GSMAK, and math. But it hurts all other data sets like Core 9 and even biology, some of the STEM data sets. Same for code experts. It has significant boost on coding tasks, but basically for all other data sets, it drops the performance significantly. So these are how the individual models look like. Yes?
Pre-trained physics model versus using an orientation model methods of continuous pre-training?
Yes, that's a great question. Like how the model performance would look like if we have included this silo data set from the pre-training stage. Yes, we don't have that model, and actually one reason we couldn't train the model was it was literally not possible. Some of these data sets were proprietary, so that we cannot really include in the initial model. Cool. Now let's look at what happens if you start to merge these models into a single model. And let's look at the two prior work I described earlier, weight merging and ensembling. And I put ++ on each of these models because we didn't actually do knife weight merging and knife ensembling. We engineered these baselines heavily to make it a very competitive baseline. For instance, I'll probably not go over details, but ensembling, we find weight, and then for every query, we find top 2 relevant domains, and then activate those 2 only, and then do ensembling. So it has a lot of hyperparameters that we engineered. So in terms of result, what we found is that the weight merging is actually not very effective. And we find this surprising because we know weight merging is very effective in a lot of scenarios. So our conclusion is weight merging helps on specific cases, like when the model was trained on data mixes that are not too different from each other, or if you're merging 2 experts. However, if you're merging more than 2 models, and when each of these models that you're merging are coming from very, very different distribution, then weight merging doesn't work that well. And in contrast, ensembling baseline was actually stronger than we thought. It's a very simple baseline, but it boosts performance by a significant margin on almost all data sets. So this was a very strong baseline. Yes, question? Yeah, that's a great question. So I would say the training cost, in terms of training cost, they're all very similar because they're developed in the same way. That's a great question. That inference cost can be different. For instance, ensembling requires 4 passes, so it could be 4 times more expensive. It's really hard to have exact fair comparison between different models because they're just very different models. For instance, we tried to think about the other baseline that may have similar inference cost than with ensembling, like maybe mixture of experts, but the mixture experts are significantly more expensive to train. So none of them are actually exactly comparable.
One basic majority vote or something, like some basic inference,
Yeah, great question. So actually, one of the we can think of ensembling as sort of the majority vote because we can think of weighted averaging over output as ensembling. Okay, I'll continue. Yes, so weight merging was not good, so we dropped this baseline and just keep ensembling ++ as our main baseline. And now I'm gonna keep adding the baseline. We compare with BTX. It's one of the represented work in MOification that I described earlier. But as I mentioned earlier, MOification as it is not really applicable to our setup because it requires training the router over all data sets jointly. So we use a variant of it where the router training is done on the public shared data only, not jointly. And that performance was not very good, worse than ensembling. So it really means the router has to be trained jointly on all data sets. If you're just training on public data, it doesn't work very well. We also have BTX++, which we improved over BTX just to make it a stronger baseline. I'll not go over the details. It's just that we engineered which layers to freeze or not. it did improve performance compared to the original BTX, but was still not better than ensembling. Now here is our model, and in particular, this version is our model that does not have router training. So this is a model that uses IDEA 1, but not IDEA 2. And you might want to use that if you don't want to go through any router training. We found that this model is a bit better than ensembling, not significantly better, but even when you do not do any router training, it's already working. And then if we combine IDEA 1 and 2 by training the router on proxy data, then it significantly helped. So for most of the data sets, we are able to get much better performance. If you look at the average number, remember that our real baseline is the previous public model that is trained on public data only. If we compare with that model, we have 27% relative gains. Yes?
What's like the shared upper bound baseline where it's like you just pretend you can train on everything?
Yes, that's a good question. So as I mentioned earlier, we couldn't really pre-train on all data sets jointly because it was just like actually restricted. We were able to have like semi-upper bound, which is we train each model, we merge them, but then we just train the router on a union of siloed data sets. When we did that, that performance was actually not significantly better than our model. So our model is already pretty close to that upper bound. I only have a few slides left, so let me finish and then get more questions. So that was like a summary of our result. I want to highlight a few key findings. So one of the findings, which is probably expected, is the largest gains are coming from benchmarks where one of the silo data sources are helping a lot. For instance, we have a lot of gain on MMLU biology and CS because these textbooks really helped those benchmarks. And we have a lot of gains on Big Bench Hard because math experts really helped. So it is directly showing our hypothesis that proprietary data sets help a lot of key benchmarks. Another thing that was less expected, and I was positively surprised, is that there is significant gains even when there is no single data source that helps. For instance, if we look at Core 9, actually individual experts is all dropping the performance compared to the public model. But if we merge these models all together, then this is much better than the public model. Same is happening for MMLU health. There is no data set that is significantly relevant to health, but the combined model is much better. Same for politics. We don't really have any data sets that are related to politics, but the combined model is better, or at least comparable to the public model. And I think the reason this is happening is because the average number can be misleading. So what's probably happening is that there are some queries that still benefit from some of the silo data sources, but also other questions that do not really benefit from them. So if you average, then you don't really see gains. But when you use the mixture of expert architecture, then you can get best of both worlds for every query. So the aggregated number can be much higher. The last thing I want to mention, which we were a little disappointed, is that for specialized tasks like GSMA-KE and coding tasks, we were not really better than the experts. So we were still significantly better than previous public model, which is a good news. But we were hoping it would be as good as some of the experts like math and coding. However, that's not really the case, meaning that we are probably losing something when we are merging the model. And we think this is likely to be because the router is not perfect. Since if the router is perfect, we should be at least equal to each of these experts. So this means there is still some room for improvement. Cool. I'll just give a quick summary and some open questions. So to summarize, I talk about the project where the goal was to make use of proprietary data sets with restrictions, such as the data sets are completely siloed, training should be in isolation. And our goal is still to have a better public general purpose model. We surveyed existing approaches like model merging and added 2 key ideas to make it really work for our setup, especially MOE-aware, silo training, and obtaining proxy data for router training. And our results show that on our experimental setup, which is pretty realistic, consisting of real proprietary data sets or simulated data sets with realistic domains, we are seeing pretty significant gains, 27% relative gains compared to the previous public model. I want to end with some open problems and then maybe take more questions. So one of the open problems that I think is pretty pressing is, as I mentioned earlier, we're still not as good than the specialized experts on some of the specialized tasks. So how can we really be better than those specialized experts could be one open question. The second thing, which I think is pretty fundamental about the current architecture, is how can we adopt fine-grained data sets and scale the number of data sets? So actually, if you recall our architecture, it's very, very difficult to scale the number of data sets because every time you add a new data, you're making a copy of the original data. So this whole model can be too big very quickly. I think probably the way to address this issue is when the base model is a fine-grained mixture of experts so that we can only add a small expert every time we add a new model, new data. But this requires pretty significant change in the base model architecture, so I think this is a longer-term goal. And the third open problem is how can we completely remove router training so that we don't need to do router training after merging, so that the router will be completely non-parametric. And I think especially the second and the third one, if you do scale the models a lot, then it may look like a retrieval model. So this is basically becoming like a retrieval model where you have a large set of experts that is trained on each of the siloed data sets that are very easy to modularize, and basically you're retrieving which experts to use. So I think these are some open questions, and that's it. Thank you for listening, and I'll take questions.
I'm surprised you said that it will look like a retrieval model, because at the end of the day, if it is using some kind of base language model, you're expected to do some kind of generalization, right?
Yes. So actually that's one motivation we are doing all of this without retrieval, because you definitely need to train some parametric model in order to generalize and do reasoning. But in the extreme case, let's say each of the silo data set is one data point. Then it's actually equivalent to the retrieval model because you're retrieving the relevant data point. So I think in the extreme case where you're extremely fine-grained and there's many number of experts, it can look like a retrieval model. Maybe the solution will be in the end somewhere in the middle or hybrid. Yes.
Thanks for the great talk. I was thinking that the motivation of this part is that we want to train the model as a lazy today, right? So which makes me expect that the performance should be, most of the performance should be at the same level or slightly lower than than expected. But it turns out that the most of the performance are higher. So do you think that this should be kind of like a new data curation method or model training, a new data creation and model training strategy that we can follow up later?
I said, yeah, great question. First of all, I think you're right that our combined model is better than the individual models that is trained completely in isolation. Something I'm not exactly sure if you assume that all data sets could be trained all jointly, then whether it would be better. That's some upper bound that I think I got a few questions about, but we couldn't really have. So that I think is a bit unclear. However, I do think there is also a possibility that even without this data restriction, it could be a new way of training the model. For instance, our recipe can be seen as an efficient way of training the mixture of experts because by default, mixture of experts requires synchronized training over all experts, and it is very expensive. So in some way, we can think of it as like an alternative way of training on MOE.
This is slightly more about like the merging stuff in general, but like what do you feel is the main bottleneck to being able to do just like highly distributed model development, where like people who aren't even necessarily like coordinating a priori like beforehand could merge their efforts like down the line by like doing some kind of model version or ensembling?
Yes, great question. My personal opinion is I think weight merging or ensembling, where a lot of work is based on, are likely to be pretty restrictive because, as I mentioned, if each models are very different or if the number of models to merge gets significant, then I think weight merging is unlikely to work. So I feel like some architecture that looks like mixture of experts seem more promising. But I think it has like a lot of technical problems, and I think in particular one thing which I also mentioned in the talk is router training. Even when individual experts are pretty good, it's really the router that has to decide which experts to use, and the router decision seems to be easy to be suboptimal. So how to do that seems like an important problem. You also made an assumption that we are merging models that did not think about coordination, so train in isolation, but I also feel like if our goal is for many different models to coordinate, then it also makes sense that even when we do isolated training, it's good to consider that, which was like one of the ideas we mentioned was about.
Yeah, we have time.
Yeah.
Yeah, so I think in this work and also in lots of the MOE work, there come motivations. All of the routers are simply like a sort of a linear layer. Given that you mentioned router is very important, is there a reason that we always just increase the linear layer for router?
Oh, I see. So maybe we should increase the model complexity?
Or is that like been just curious about like why everyone's
I see. That's a great question that I don't really know. Yeah, I think people use pretty lightweight router. I think one thing that seems underexplored and could be interesting is if you can use some like external information about different experts, like maybe use embeddings to initialize. That could be one way to improve the router. Yeah. Also, I think for regular mixture of experts where all models are trained jointly, then the router problem is a little different from diff keys because everything is trained jointly and we don't really have a notion of these experts just specialize on one thing and the other experts just specialize on the other thing. That could be one reason to. Yeah.
So right now, all experiments are basically based on the corpus with different topics, right? I'm wondering if this kind of silo system, this corpus are separated a different way. Let's say one corpus actually have all the math coding, but they're on a slightly different domain. Do you think all the observation might transfer to like a different way of separating the data? Because I would imagine maybe like the router going to be slightly harder to train or something like that.
Yeah, that's a very great question. And yeah, I think that could be a very realistic setup too, because maybe different entities have their own corpuses. They don't really overlap, but maybe have similar distribution. Yeah, I think that's an open question that I don't really have answer to. If I have to guess, I feel like the merging could be easier because model merging seems to work when their training data distributions are similar to each other, but it's much more challenging when they're trained on completely different distribution. But I think this is an empirical question.
All right, if there are no other questions, let's thank the speaker again.